must say that I'm truly thrilled to have the pleasure of introducing to you my colleague, Tony Leggett, who is MacArthur Professor of Physics and Professor at the Center for Advanced Study here at the University of Illinois. Tony grew up not far from London, in England. He was a student at Oxford University, but his first degree wasn't actually in physics. Instead, it was in Latin, Greek, and philosophy. But deciding that nature would be a fairer opponent than personal opinions, Tony followed up with a degree in physics, and he stuck to that with great success. Tony's research interests range far and wide, but can be loosely assembled into three interwoven themes: superconductivity and superfluidity, which we talked about last time, manifestations of quantum mechanics at the macroscopic level, and foundations of quantum mechanics. Today, Tony has kindly offered to talk to us about the strange fate of cats and other things according to quantum mechanics. Please join me in giving him a warm welcome.
Now, the subject I'm going to talk to you about today is perhaps the most controversial problem in the whole, or certainly in the whole of physics, possibly in the whole of science. And what is genuinely surprising about it is that it is not that everyone agrees that there is a question or problem and that they disagree about the answers. The problem is that they disagree about whether there's a question there in the first place. There are many people who would feel that the whole subject that I'm going to be talking about has been completely solved and sewn up, and that therefore you and I are going to be wasting our time for the next 55 minutes. There are others, and I won't tell you yet whether or not they include me, who hold that this is one of the most profound questions in the whole of science, and in some sense, until we've got it sorted out, we don't really understand a great deal about what is going on in the real world. So let me start by showing you a very simple graph of scale of the physical world. Paul already talked to you to some extent about the idea of scale in physics, and what I'm showing you here is a so-called logarithmic scale. This one? Yes, okay. Yes, that, good, thanks. Yeah, lovely. I'm showing you a logarithmic scale of the physical world in which each step represents a factor of about 10 billion. So, for example, something on this scale here would be 10 billion times as big as something which occurs about here, and so on. Now, if we look at things in this way, then the everyday world doesn't really occupy a great deal of this scale. What's the smallest thing we might count as part of the everyday world? Well, let us say the smallest speck of dust that we could see with the naked eye. That's probably some fraction of a millimetre. And then what's the biggest thing that we might reasonably count as part of the everyday world? Well, that's a bit subjective, but we might say perhaps a town of the size of Champaign-Urbana. Okay, so crudely speaking, those are going to be different by about this factor on that graph. So this is where the everyday world lies, and you see it's actually a rather small and unimpressive bit of the scale as a whole. If we go up from here, we find that about at this scale here we get to the size of the solar system, and this around here maybe we might get to nearby galaxies, and then the size of the universe as a whole, insofar as we know it and it makes any sense, would probably be somewhere around here. If we go down, on the other hand, well, we go down a few factors of 10 and we come to the world of atoms. Go a little further, we come to the world of nuclei. And then if we go down further still, well, we're not really terribly sure what happens down there, but our particle physics colleagues tell us that they expect that indeed the scale does go on, and that, as it were, there are interesting things down here until somewhere around here, possibly, as it were, we begin to run out of scale, in the sense that there is a strong belief that when we get down to a scale of the order of 10 to the minus 33 centimeters, that's 1 10 billion billionth, roughly, of a centimeter, then maybe the whole idea of size and scale begins to break down. We get to the so-called Planck scale, when all our normal ideas give out. Why do I show you this graph? Well, what I'm going to tell you about is some of the strange implications of what most people believe to be now the correct and ultimate theory of the physical universe, namely quantum mechanics. Now, the first question we might ask is, okay, we're going to be talking about quantum mechanics. Over what scale in this graph has quantum mechanics actually been more or less directly tested? And when you ask that question, the answer is actually really rather unimpressive. Very crudely speaking, quantum mechanics has been tested in some more or less direct sense from a level somewhat below that of nuclei. That's what our colleagues in high energy physics do when they do accelerator experiments and so forth. Up to the level of nuclei, up to the level of atoms, and arguably somewhat beyond the level of atoms, but not very much. Certainly, there are no direct tests of quantum mechanics yet up at the level of the everyday world, though, as I'll show you at the end of the lecture, we are getting a lot closer to that. So when people say that why do people say that they believe that quantum mechanics is a complete description of the physical universe? Well, you might say, okay, we know it works here, so maybe what happens at the level down here, below the level of nuclei, maybe we shouldn't be too sure it'll go on working down there. Maybe not. But most people do believe that it's going to go on working up here. Why? Well, I think if you really push people, the answer is very simple. They would tell you, well, we know that quantum mechanics describes very well the world of nuclei and atoms and molecules. Well, what is ordinary matter made of? What are you and I and this desk and so forth made of? We are made of atoms and molecules. Now, therefore one would expect that if the quantum mechanics describes the world of atoms very well, and we are made of atoms, then it should, in principle at least, also describe the world of everyday life. It may be very inconvenient to have to describe it this way, but at least you'd expect it to be possible, in principle. So in other words, to put it in a nutshell, if big things are made of little things, and we have a theory which describes the little things, then we would expect it to describe the big things. Okay, so far so good. So as I say, most people do believe that, at least in principle, quantum mechanics does describe the whole world. Now, quantum mechanics has some very funny features. And to illustrate these, let me imagine that you go to a bowling alley and start playing around with the balls. Now, this is a rather peculiar kind of bowling alley. It has the property, first of all, it has the property that you have your skittles up here, but unlike, I believe, I don't do bowling much, but I believe that the idea is to knock over as many skittles as possible with one ball. This is a slightly different kind of bowling alley, in that the size of the ball and the positioning of the skittles is such that, and the way they fall back, is such that on any particular try, you hit one and only one ball, okay? So unless you miss wildly, you're going to knock one and only one of these skittles over. Moreover, you've got this little this barrier here, which has got a little hole in it. And the ball, in general, you may or may not throw the ball exactly straight, and it may bounce in various ways off the edge of the slit. Okay? So what you'd expect, crudely speaking, is that sometimes the ball goes straight through and knocks over, say, this skittle. Sometimes it bounces against this edge, goes off here and knocks over this one, or here, etc., etc. Okay, and then what you might do is you throw your ball a large number of times, and then you count how many times you hit number one, how many times you hit number two, and so forth. And then you might plot out your results. Now, don't ask me just right now why you would do such a crazy thing. Just take it from me that you might. It's the thought experiment, as we physicists say. So you plot the number of hits, say, on skittle 1, the number on skittle 2, and so forth. And you see that this has, not surprisingly, you tend to hit 4 more times than you did any of the others, because it's more or less in a direct line. But you do hit the others some of the time, because you don't get your aim quite right. Okay, so far so good. Nothing surprising at all about that. I mean, as I say, you might well ask why you'd spend your time doing this on a Sunday afternoon, but that's a different question. So let's just do something a little more sophisticated. On this, we've now slightly improved our bowling alley so that we now have, as it were, two different rooms, if you like, or two different spaces separated by a thick barrier. And the point about that is that if a ball goes through this hole, if your ball happens to go through this hole, it's bound to hit one of the skittles on this side. If it goes through this one, you hit one of the skittles on this side. And to no one's surprise, what happens here is that if you throw the ball more or less at random, then sometimes it goes this way and you hit one of these, sometimes it goes this way and you hit one of these. It never happens that you knock over more than one, and, well, rather obviously, you always knock over one on this side or on this side. In other words, your ball always does go through here or here. And the graph you plot out, incidentally, physicists call this a histogram, but you don't need to remember that. The graph you plot out might look something like that in this case. Again, not at all surprising. We now pretty up our bowling alley just a little more. Now what we're going to do is something a bit different, because now, you see, we still have our two apertures, two holes here, but in principle at least, it's possible, for example, to hit this skittle here either by going this way and bouncing so, or by going this way and bouncing so. At least that's if both doors are open. But these little handles here are meant to indicate that you can, in fact, if you want to, shut off, you have a door, as it were, which will close and shut off this hole, and similarly with this one. Now, what would you expect under those conditions? Well, first of all, rather obviously, if you have both doors closed, you'll get nothing at all, no hits at all. So that's straightforward. Suppose that I close door B so that only door A is open. What's going to happen then? Well, again, we'll get a distribution of probabilities. Sometimes we'll hit this guy, sometimes it'll veer off and hit this one, and sometimes it'll hit this one. And keep your eye on this guy, because this is the one that's going to be really crucial for our argument. So we plot again a graph, a histogram, and you see the height of the red bars now indicates the number of hits you get on a particular skittle when only door A was open and door B was shut. And you see that it's a sort of maximum around 4 or 5, and tails off rather fast as I get down into this part, which is sort of natural. Well, now let's do it the other way around. Let's shut door A and open door B. And now we would expect, roughly speaking, to get the graph shown with the blue lines here. Now, you see, you get a maximum around number 8 here, maybe number 9, and it tails off rather fast as you go to this end, that is up here. Well, still nothing at all surprising. So you might ask, why am I going through all this nonsense? Well, now let's ask the question. Now, we haven't not yet done one experiment which is really rather obvious in this situation, which is to leave both my doors open and ask what happens. What would we expect? Suppose we just ask ourselves ahead of time, what would we expect if both of those are open? Well, the top graph here is just the same as I had on my last view graph. It's just put here for convenience. The red, remember, is the number of hits you get with only slit A open. The blue is the number of hits you get with only door B open. Now, if we open both doors, what do you expect? Well, unless something very peculiar is happening, you'd presumably expect that the number of hits would be simply the sum of these two graphs in each case. So we add these two graphs together, and we get the graph approximately which is shown here. And now you see, crudely speaking, we expect to get a maximum somewhere around pin 6, which remember was roughly in the middle, because in this case we can hit it, we have an appreciable chance of hitting it through either door. Okay? So fine. That is what we would expect. Now, let's suppose that we actually do this experiment, and what we actually got, just suppose, we did this experiment with both the doors open, what we actually got was this. So you see, we've now got more hits than we expected in the wings, as it were, but in the centre, on our crucial pin 6, which remember was the centrally placed one, we've got no hits at all. Now that is very surprising, if you come to think about it. Because, well, we had plenty of hits on pin 6 when only door A was open, we had plenty of hits when only door B was open. When we open both doors, we get no hits at all. And that is very, very surprising. Or it would be if we were indeed to get that result. And you might think, well, maybe there's some kind of funny mechanical effect. Maybe by opening the door number A, I somehow blocked door number B in a certain way, or I changed the shape of door number B. That's something you could actually check. And let's assume that doesn't work. that there's no observable effect on the shape of door B. Then you might think, well, perhaps I've been sending off the balls too quickly, and some of the ones which came through through door A have bounced off some of the ones that went through slit B. Okay, but no, I mean that can't be true because I can just I can roll the balls very infrequently, so that I only have one ball at a time. You know, by the time I throw the next ball, the first one already knocked down its skittle and gone way off and been collected. So if this were to really happen in a bowling alley, you'd really wonder, as it were, what you'd been drinking the night before, I think, because something very odd indeed would be going on. Well, alas, as you're probably anticipating, this is precisely what happens at the level of atoms and molecules. Let's imagine, now we're getting much closer to real physics, as it were. Let's imagine that we have some kind of source of some atomic particle, like say an electron. Let's just think for definiteness about electrons. And suppose that we fire off these electrons in such a way that they can either go down a path through B or down a path through C. And imagine, I haven't actually drawn this in so as to avoid obscuring the diagram, but suppose there's some kind of wall here, just as there was in remember I had my, just to show you once more, I had my my bowling alley picture in which I had something like this, right? So imagine that there's some kind of wall like that, so that we know for sure that if a particle went this way, it will get into this detector here, and vice versa, if it went here, it'll get into this detector here. And for the moment, we just think about these detectors as simply some kind of black box, which are either going to click, telling us that a particle has come out here, or they're not going to click, telling us that it hasn't. Right? So imagine that we have this set up, and we turn our source on. And imagine that we turn it on in such a way that we only get one electron at a time. They come out very slowly. It's possible to do this. What do we see? Well, what we see is that each time an electron comes out, and in principle we could check when one does come out, but let's imagine we've done that. So each time an electron comes out, we ask, okay, what's going to happen? What we find is that either this detector clicks or this one clicks. That you never get neither of them clicking, and you never get both of them clicking, at least if you set the apparatus up right. So in other words, every electron which comes out apparently either went this way or went this way. There's no question of, as it were, half an electron going this way and half this way. Always the whole electron does one or the other. And I've said atom here, but it comes to the same thing. Each atom either takes path B or takes path C. Not very surprising. Well, what happens now if, rather than setting up the experiment this way, we do something more like our really interesting bowling alley experiment, where we allow the electrons, or atoms, to get to a single detector here. That corresponds roughly to our pin number 6 in the bowling alley experiment. We allow it to get there by either of these two paths. And we don't do anything special here. We just let it go through, as it were. Then what we find is that the probability, or if you like, the number, it doesn't really matter, we can talk about either, the number of electrons which arrive here is not simply the sum of the number which arrives through here and the one through here. In other words, we can do the following set of experiments. We first shut off this path C. How do we do that? Well, we put in some kind of absorbing material or whatever. We can check that it works as advertised. So, we cut this path off, and in that way we measure the probability, or the number, which go from the source through B to D. That's this quantity here. Similarly, we shut this one off. We can measure the number which go through here. That's P. S goes to C goes to D. But now, when we open both paths, we find that in general, the probability of getting from here to here is not simply the sum of the probabilities of going this way and of going this way. And in fact, if we set up our apparatus right, we may even find that although then when we had only this path open, a finite number of electrons got to here, and when we had only this path open, a finite number got to there. Nevertheless, when both paths are open, no electrons whatever get to there. So that's very surprising. It's exactly the analog of the thought experiment which I mentioned to you in the bowling alley. So what's going on? Well, again, you might think maybe somehow by opening this path we affected this one. And But again, that's something that you can, in various ways, check. And it doesn't seem to be happening in the experiments in question. Again, you can say, well, maybe the electrons were coming out too frequently, as it were. They were obstructing one another's paths in some way. But again, you can do that experiment in such a way that only one particle is in the apparatus at one time. And in fact, if you do it with neutrons rather than atoms, while one atom is going through the apparatus and arriving here, one neutron rather is going through the apparatus and arriving here, the next one is still sitting in the uranium nucleus in your reactor. So there's just no way that we can see it could be affecting what's going on. So whatever is happening does seem to be happening as a result of the behavior of single particles and not of some kind of interaction between lots of particles. Well, at this stage, we think, where have we seen something vaguely like this before? And, well, one place that we might look, and in fact, this becomes more obvious if you actually do the experiment, because what you actually see is that a lot of electrons arrive here, a few here, a lot here, a few here. And so if you actually had a photographic plate, you'd see dark and bright lines on your plate. Now, what does that remind you of? It reminds you of the kind of interference experiments that you do in optics or in more generally with waves. So at this point, let's just think a little about the way in which waves behave. It's not obvious why that's going to be relevant, but let's just think about it. So let's first just think a little about the way in which waves interfere. Could we have now the ripple tank demonstration? Yes. Okay, now here we have, what we actually have here is a ripple tank, a tank of water, and at the, you can't actually see it on the screen, but at the back there is this oscillator which is going up and down and sending out waves. And you see that the waves, as they come, you can see the crests and troughs of the wave coming forward, and you can see they're more or less straight lines, more or less planes there. Now that you come to these two slits, and now you can see that when the wave gets here, it more or less starts to spread out, more or less uniformly, not quite, but more or less uniformly, and similarly here. But the point I want you to focus on is that here, as it were, across one wave, the lines are more or less of the same thickness. It's not terribly clear, but I think you convince yourself of that. In other words, the height of the wave is roughly the same all across this plane here at any one time. On the other hand, when you get down here, it's not, again, it's not something you can read off quite immediately, but I think you can convince yourself that the pattern is considerably darker down here than it is over here. And crudely speaking, that indicates the height of the waves down here is a lot larger than it is here. Now, why is that? Well, crudely speaking, as we know, it's because the crest of a wave coming from here coincides with the trough of a wave coming from here, and so the total wave is always rather small. We'll come back to that point in a bit more detail in a moment. Okay, could we now have the loudspeaker demonstration? Now, what I want you to do is to move your heads sideways, like so, and see if if the loudness of the sound actually changes very much. Okay. Okay, thanks. I think I had a chance to do that. Now, how many people found that it did change substantially? Yes, I was afraid that would happen, actually. Yes, I'm afraid that because of the actual design of this lecture hall, you're getting a certain amount of interference even with one speaker. But now, if you switch on both the speakers, we now have both of them switched on. Do it again and see if you have a substantial difference. Okay, so thank you. So how many had a substantial difference this time? What you're seeing there, basically, or what you should be seeing if the experiment is working perfectly, is that if it weren't for the details of the shape of this lecture hall, a single loudspeaker would send out a wave whose crests are really about as high in all directions. But two loudspeakers, although each of them sends out crests which are the same height, in some places the two crests will arrive together, and so you'll see a much bigger wave. At other points, a crest from one will arrive in coincidence with a trough from the other, and so there'll be no wave at all. And ideally, you shouldn't hear anything. And in fact, I think you'll find that there are points. I actually did this myself yesterday, and there certainly are points where you can hear very little, if not actually nothing. So basically, these illustrate the qualitative features of wave phenomena. And that's fine, I think, thanks. what I'd now like to talk about is wave phenomena a bit more generally. And what I want to emphasize is that really, when one says wave, one thinks of something which goes like that. Okay, but that really isn't essential to the idea of a wave. What's essential to the idea of a wave is, first of all, something, as it were, which can exist throughout at a whole lot of different points. So, you know, wherever you were sitting in the audience, you heard the sound. And secondly, most importantly, that there is something connected with a wave which can be either positive or negative. Okay? So, for example, in the ripple tank, it was the height of the water above the background. Okay? That could be either positive for a crest or negative for a trough. For a sound wave, it actually turns out that what's the quantity which is positive or negative is the excess pressure above the background pressure of the air. And because the wave is described by a quantity which can be positive or negative, which we usually call technically its amplitude, that means that two waves can interfere in such a way that they cancel. And let me just show you. I'll show you this using a different example, which I can't, unfortunately, haven't been able to build or illustrate. If any of you ever happen to be in Munich, in Germany, do go to the Deutsches Museum there. It's a big science museum, and they do have, among other things, this demonstration. But it's just rather complicated to build for present purposes. So imagine now we have a stretched string, like a violin string, say, and you have two pegs at the end, which can wobble somewhat, and you can twang them, and then see if the peg at the other end twangs. Now suppose I twang this peg here, and send a disturbance of my wave, which I've exaggerated it tremendously, of course, but it looks something like this, okay? And I send it down to the other end. Well, it'll have an effect on the peg, and the peg will start wobbling backwards and forwards, and start vibrating. Now suppose I do it again, but this time I send down a negative pulse, like so. Again, it'll go down, and again the peg will be vibrating, although actually in a slightly different way, as it were, as we say, out of phase with the first one, the first case. But now, suppose that I actually somehow manage to produce both a negative and a positive pulse at the same point and travelling in the same way. Then clearly, well, I don't know if it's clear, but it's at least plausible that that is equivalent to not having any disturbance at all. These two have just cancelled. And so a positive disturbance plus a negative disturbance equals no disturbance at all. Now, how might we actually generate this situation? Well, let's have a slightly more complicated setup. Let's imagine that we have a three-peg setup now, but there's no peg here. There's no peg at the join here. That's very important. These are just three strings again. So I now do three experiments again. First of all, I twang this peg here, and I send a positive disturbance down this string. Now, just for illustration, suppose that in fact all of that little disturbance travels on down the string here like this. Okay? As I say, it won't really, but I don't want to complicate matters. Then in fact it travels down, and when it gets to this peg starts vibrating. So you see something here. Suppose, however, now that you pluck your bottom peg here and send a negative disturbance down here. Then again, that negative disturbance will go on, and again, this peg will start to vibrate. So in both cases, something, as it were, certainly some kind of influence, some energy, if you like, has been transmitted, and also in this case, it's been transmitted. But now, suppose we were to do the following. We actually combine, as it were, these two situations, and we, let's see, I want to cover this for a moment. We send a positive disturbance down here and a negative disturbance down here. Now what's going to happen? Well, we said, I mean, in some sense, both of them are going to go travelling down, but we said that if I just put this one like so, and this one like so, then that's equivalent to having no disturbance at all. So there is no disturbance which goes on down the string, and this peg here is totally undisturbed. It does not vibrate. Okay? Now, looking at that, you might well worry about something, because after all, something, as it were, has travelled down here, and something has travelled down here, and yet neither of them have come out down here. And in particular, if you're a physicist, you would worry about what's happened to the energy involved in those pulses. Where's it gone to? It can't just disappear. Okay, well, the answer is rather amusing. As I say, I haven't done this technically correctly, but crudely speaking, what happens is that the energy, in this case, if I start off like this, what happens is these pulses don't get down here at all. They get rather reflected back, and back to the pegs they came from. And as I say, we could go into that more technically, but it's not worthwhile for present purposes. So, the point I'm trying to emphasize here is that wave-like phenomena in general, can show cancellation effects. And if you think about it, that's precisely the kind of effects, qualitatively, which we would need to account for these peculiar phenomena which occurred with the atoms. So let's see how that works. As I say, we now have a very well-developed theory of what goes on at the atomic level, quantum mechanics. So what does quantum mechanics say about this, this peculiar experiment with the two paths? Again, we have our source of atoms or electrons. We have two possible ways of going, through path B or path C. And of course, I don't have to go on to the detector here. I could go elsewhere, but imagine that I'm interested in cases where I do. So again, I can arrive at D either through path 1 through B or through path 2 through C. And now what quantum mechanics says about this is that there is a certain amplitude which you can think of as like the height of a wave, something rather like the height of a wave, to go from here through here to here. So you can think very intuitively about a wave which is propagating here. And similarly, you can get a wave which is propagating here. Now, if I want to know what is the height of the wave which arrives here, that is the amplitude to go from S to D, then what I've got to do, according to quantum mechanics, is to consider both possibilities and consider the amplitudes for each of these, and then add the amplitudes. That's like considering the waves, the water wave, for example, which came through slit 1 and working out its height here. Consider the wave which goes through slit 2 and work out its height here, and then you add the heights of the two waves together to form a total wave, okay? And what is really essential here is that by its nature, this amplitude is supposed to be wave-like in the sense that it can be positive or it can be negative. And so, so what I will do then is to add the two amplitudes for these two processes separately, that is, if you like, the two waves coming through these paths separately, to get a final amplitude, a final wave height at here. And then the next thing that quantum mechanics tells me to do is to calculate the total probability of arrival here by simply squaring the total amplitude. So for those of you who are familiar with the classical theory of waves, that's a bit like getting the energy of the wave by squaring the amplitude. But in this case, it's not an energy, it's a probability of arrival. That's the funny thing about quantum mechanics. So in this case, what do we do formally? Well, we say A, the total amplitude to go from S to D, that, if you like, the total height of the wave at D, is the sum of the height of the waves coming through path 1 plus the height of the waves coming through 2. And remember, as I say, it's crucial to remember that these can be positive or they can be negative. So now we're going to square this up to get the total probability of arrival here. And that's just the square of this total quantity. So just the square of this sum. Now you just do the little bit of arithmetic involved, and you find A1 squared plus A2 squared plus 2A1 A2. Now, A1 squared is simply the square of A1, which is the amplitude to come through here. So if only slit 1 is open, then we only have A1, and the probability is just A1 squared. If only 2 is open, we only have the amplitude A2, and the probability is A2 squared. So P1 plus P2, as it were, the sum of the probabilities of coming through here to here, are these two terms. But we now have this extra term here, 2A1, A2. So in general, that is not going to be 0. And depending on whether A1 is the same as A2 or minus A2, you're going to get quite different results. If A1 is equal to A2, both in magnitude and in sign, that means in effect two crests come in together, then you actually get A1 squared plus A1 squared plus 2A1 squared, which is 4A1 squared. So that's more than you would have got through the two paths separately. If, on the other hand, A2 is minus A1 and equal to it in magnitude, you get A1 squared plus A1 squared minus 2A1 squared, and that's 0, right? So in that case, we get we get nothing arriving, no electrons arriving at our detector here. And so this then, this general scheme gives at least a consistent account of why this phenomenon, why we get this peculiar phenomenon. However, we might ask, well, what is this amplitude? Is it like the height of a water wave? Is it like the surface pressure in air? And the embarrassing answer is that no one knows. No one knows whether it exists, and no one knows whether, if it does exist, what it is. So, nevertheless, the calculations you do using this seem to give very, very good agreement with experiment. So it's very puzzling. Now, one thing I want particularly to emphasize here, in order to get this result, and in particular, to get the result that under certain conditions, no electron arrives here, it's got to be true that for each individual electron going through the system, both A1 and A2 exist and are not zero, okay? Otherwise, if either of them were zero, this term just goes away and you get the usual results. And let me emphasize again, that's got to be true for each individual electron that's going through there. It's not enough saying that, well, sometimes A1 is non-zero and sometimes A2 is, okay? Well, at this point, this is very peculiar, because basically what we've got here is that you remember that if we actually didn't do the experiment in this form, but rather looked to see, we put our detectors here and here, then we always would find, apparently, that each electron either took this path or this one. But now, the fact that you've got both these quantities occurring indicates in some sense that each electron, as it were, had something about it which went through here, and something about it which went through here. So, no, that's very mysterious. And yet, when we get to the detector, the electron always registers itself in one piece, as it were. It doesn't split. It always arrives in one piece. So, well, now there's an obvious question that arises. Why don't we just look to see? Like, we do this experiment, but look to see, in each case, which of these poles is followed. Well, how might we do that? Well, you can imagine yourself taking a flashlight, say, and shining your flashlight on one flashlight on here and one flashlight on here, so that you actually see the electron, as it were, going through one path or the other. You can't do quite that, but you can do something pretty close to it in practice. What do you see if you do that? Well, under these conditions, each electron seems to take either path 1 or path 2. That is, you either see the electron there or you see it there. You never see it at both and you never see it at neither. Okay, so you say, well, what happens here now? Do you still see the interference? And the answer is no, you don't. Under these conditions, the probability of going from S to D is simply indeed the sum of going through these two paths separately. That is, you just get back the common sense result. So this really is becoming very puzzling indeed. Basically, whenever you force the electron, as it were, to declare whether it went this way or this way, it will always tell you one answer or the other. But if you don't force it to declare, then it will show you effects which seem to be saying that in some sense it went through both, or maybe neither of the two possibilities. So this is then the conclusion from experiments at the atomic level. If we consider, this is just summarizing what I've said in the last few graphs. Consider a collection of systems, for example electrons, each of which has two alternatives open to it, say two paths, B and C. If we look to see which alternative is realized, then each electron appears either to take path B or to take path C. However, if we don't look, then the subsequent behavior at the detector indicates that, well, I don't know how to say it. You should either say that both B and C were realized or neither B nor C was realized. But you most certainly cannot say that each electron realized either B or C. That's the one thing you can't say about that situation. Now, say, quantum mechanics, supplemented by the standard measurement axioms, by which in this case I mean the axiom which says that the probability of arrival is just proportional to the square of the height of the wave, quantum mechanics does give a coherent account of how that can happen. And so if you are prepared just to take the notion of measurement for granted and assume that your black boxes work as the manufacturers say they should, and so forth, then basically you have no, well, you've got a very peculiar situation, but at least it's confined to the level of electrons and atoms. And for many years after quantum mechanics was developed in the late 20s, Niels Bohr and Heisenberg and various other people insisted on this point of view. They said, look, you shouldn't really even try to describe nature at the atomic level in ways which make any sense in everyday terms. Rather what you've got is you've got your measuring apparatus, which is a nice sort of big black box of a sort of visible size and so forth, and that's a purely classical everyday object. And then you have the quantum world of electrons and atoms, and really all that these electrons and atoms are doing is merely to make some connections, if you like, between the macroscopic objects, your measuring devices and so forth. And so you shouldn't worry too much if at this level nature seems to have some very peculiar properties, because after all, they're never going to, in any sense, come up and infect the level of the everyday world. So like Paul's ants, you know, they're something we don't really have to worry about in the foreseeable future. But unfortunately, there is a snag. The snag is basically connected with when things happen in quantum mechanics. And there's a very famous illustration of this, which was given in a paper by Schrödinger way back in 1935 and has caused furious argument ever since. Basically, the problem is that there is no point in some sense, we agreed that quantum mechanics, hopefully you agreed with me, that it's plausible that quantum mechanics is a complete description of the whole world. If it's a complete description of the whole world, then it's not only a complete description of the electrons and atoms we're doing the measurements on, it's also a description of the black boxes, the Geiger counters and photographic plates and so forth that we're using to make the measurement. After all, they're just made up of electrons and atoms and so forth, so why not? No, so we've got to be, in principle, able to apply quantum mechanics to the whole caboodle. So now let's imagine the following setup. We have our source, and we're calling it A now, and we have two paths which a given atom can follow. And behind the two points B and C, we put detectors. Now, we said that we just took for granted that if we did this experiment, either this detector would click, or this one would. However, as I say, in principle, we ought not to say that. We ought to examine the possibility of describing the whole setup by quantum mechanics. Let's, for the moment, assume that we cut off this path, so that our atom certainly went up here. Then we arranged this detector so that nothing particular happens. I mean, it just clicks and life goes on as before. This one, however, is more interesting. If we now shut off this path so that our atom certainly comes down path C, then this detector will click, and then something a bit more serious is going to happen. We have this detector wired up to a closed box in which there is a cat and a vial of cyanide, and there ought also actually to be a gun which can blow openly. I forgot to draw that in, but you should have a hammer which smashes the vial of cyanide. And of course the point is that if the atom now comes down this path, the detector is triggered, the electronics works, the hammer falls, the cyanide is blown open, and the unfortunate cat dies. Now, this is the most famous animal in the history of physics, most certainly. This, as I say, was first proposed by Schrödinger as a thought experiment. Owen Schrödinger, who was himself a founder of quantum mechanics. And he proposed this as a thought experiment, and ever since then it's been known as Schrödinger's cat. So we now have two states which are very different and quite easily recognizable. You know, you just look in the box and you see whether the cat's alive or dead, and these are going to result from different behavior of the atom. So what's the problem? Well, as I say, the problem is that at least in principle, we should be able to describe the whole setup in quantum mechanical terms. It may not be very convenient, but it must be at least a legitimate demand that we can do it. And now this one is not, this photograph incidentally is not in the sheaf you've got. It's one I made up later, but it's a rather important one. We have a basic and non-negotiable principle of quantum mechanics. Namely, if state A leads to state A prime, and state B leads to state B prime, then it's quite inevitable within the framework of quantum mechanics that a state in which both A and B are represented leads to a state in which both A prime and B prime are represented. I'll say that's a very fundamental principle. If you don't accept that, well, you're free not to do so, but you are not then doing quantum mechanics as it's normally understood. So if we believe that quantum mechanics is indeed a description of the whole universe, this had better be true. Well, what happens if indeed it is true? Well, if A1, if the state, if we now have a state in which both A1 and A2 are represented, and we saw that we had to have such a state in order to get the interference effect, then in this situation, A1 leads to an amplitude for the cat to be alive, A2 leads to an amplitude for the cat to be dead, and therefore both these possibilities are still represented in the final description of the universe. So in other words, we now have what is called a quantum superposition of two states, namely cat alive and cat dead, which are macroscopically distinct. That is, they are recognizable as different at the everyday level by the naked eye, and so forth. So we've produced this weird description in which, as it were, there is some element of reality associated with the cat being alive and some element of reality associated with her being dead, and both of them are still, in some sense, really there in the real life situation. Now, clearly, that is a very uncomfortable situation for the cat to start with. It's even more uncomfortable for the physicist who has to contemplate it, because we all believe, or we all think we know, that if we were to take the lid off the box and look at the cat, then she would either be alive or she would be dead. In fact, we wouldn't even know how to recognize a state of this kind. So what basically we've done is to force quantum mechanics, by extrapolating it up to the level of the everyday world, we've forced quantum mechanics to give us a description of the everyday world, which is quite at variance with our ordinary common sense ideas. Okay? And this is the basic Schrödinger's cat paradox. Now, as I say, many people think that this really is not a problem at all. Why do they think that? Well, there is a so-called orthodox, what I call an orthodox interpretation of the Schrödinger's cat paradox, which goes something like the following. Recall our simple experiment with atoms, say. So we have two paths, or two possibilities, and we had to add the amplitudes for each of them, and then we got P1, which is A1 squared, the probability to go this way when only this way is open. We got P2, which is the probability to go this way with only this way open. And then we got the so-called interference term, which involves both these amplitudes, A1 and A2, simultaneously. And now we notice that if A1 was equal to plus A2, we got an increased probability of arrival here, whereas if A1 was minus A2, we got 0 probability. And now the argument goes something like the following. Fair enough, that's what happens at the microscopic level, the level of atoms and electrons. But now imagine that we go up, we try to push quantum mechanics up to the level of cats and so forth. Then it's claimed the interaction, cats are such messy beasts, I mean messy in the sort of conceptual sense, they're such complicated beasts, and they're such, we know so little about their exact initial state, and we don't know exactly how they're affected by the radiation field, and so on and so forth. Because of all these unknowns, basically the signs of A1 and A2 are random, and then we must average over those random signs. Now, the average over A1 squared is just P1, the probability of going through this path when only that is open. The A2 squared average is P2, the probability of going through this one when only that is open. But because the sign of A1 relative to A2 is random, A1 may be either plus or minus A2, after averaging we find that the average of this quantity is 0. And therefore the so-called interference term goes away, and we recover the common sense result that the probability of going from here to here is just the sum of the probabilities going by the two paths. So it's then argued that, so I don't think this technical result is much disputed. Not many people deny that, the technical result. What is then argued is that since we can no longer see the effects of this interference term, then it is legitimate to say that by the time we get up to the level of cats and so forth, either one of these paths or the other is always followed. In other words, and in particular, Schrödinger's cat, each particular Schrödinger's cat either is alive definitely or is dead definitely. Now, I say that argument is complete nonsense. Why do we not believe that one path or the other was followed at the microscopic level, the level of atoms and electrons? Answer, because we actually see the effects. We have evidence, positive evidence against it. The evidence being the interference, which is described technically by this term here. But we actually see, we don't have to use quantum mechanics, we actually see directly, by direct experiment, the effects of interference. Now, as we push up towards the everyday level, quantum mechanics itself, the framework of quantum mechanics, has not changed at all. All that's happened is that it is claimed, and I believe correctly claimed, that this term basically averages to 0, so the evidence which was there at the level of atoms and electrons is no longer there at the level of cats. Now, does the fact that the evidence that a particular interpretation of quantum mechanics is not right, the fact that that evidence has gone away, mean that we can now start to use that interpretation? Okay? In other words, let me just go through, this is a crucial point, so let me just, the possible expense of boring you, just go through it once more. We believe that at the level of atoms and electrons, it is not correct to say that each electron either took this path or took this path. And certainly it's not correct to interpret the quantum mechanical description as saying that. Why not? because of the experimentally observed phenomenon of interference. By the time we get to the macroscopic level, nothing has changed in the formal structure of quantum mechanics. However, the evidence of interference has vanished. So can we now go back and say that each cat either was alive, as it were, or was dead, took one path or the other? I claim not. Imagine that we have a murder trial in which there's an absolutely cast-iron piece of evidence against the accused. Let's say he's accused of murdering his wife, say, and there's a hatchet with her blood on it and his fingerprints all over it, etc., etc. Absolutely cast iron. Everyone says it's obvious the guy's going to be convicted. Halfway through the trial, this crucial bit of evidence suddenly, mysteriously disappears. Now, it may well be the case, I don't know exactly what the law is in this kind of circumstance, but it could be the case that formally the jury has to declare the guy innocent under these circumstances. But does anyone really believe that the fact that the axe disappeared meant that he suddenly changed from guilty to innocent? Clearly not. And that's precisely the argument which people are making here. Basically, the fact that the evidence has disappeared means that we can suddenly reinterpret quantum mechanics in a way which we couldn't at the level of electrons and atoms. If you don't believe that solution, then there are a whole set of other solutions on the market. And let me just very briefly describe some of them. There are two types of solution, really, depending on whether you keep quantum mechanics as a complete description of the world or whether you decide to abandon that assumption. So let's go through the first. First of all, there is an interpretation which says that, look, you're really taking all of this much too seriously. These amplitudes have no physical reality at all. They correspond to nothing in the real world, and therefore no argument which is based on them can really have any force. All that quantum mechanics ever is a sort of cookbook recipe designed to produce probabilities of getting particular results in experiments. And that means actually probabilities of really seeing that a particular cat is alive or dead or whatever. So just, as it were, don't take it seriously. Just use it as a calculus, as a cookbook recipe, like the ancient Chaldean astronomers' recipes, to get the actual physical predictions, and then throw it away. Now that perhaps is consistent, at least. It has no obvious internal inconsistencies, but there's something very peculiar about it, because you have this. Quantum mechanics introduces this idea of an amplitude, a sort of wave-like entity. And everything in it, basically, all the interesting results come out precisely because you take that entity seriously. And now you're supposed, at the end of the day, to say, oh, forget it. It didn't really correspond to anything in the real world. It was just a calculation recipe. I find that really rather hard to believe, to be honest. If you don't go for that, then there's some much more exotic interpretations on the market, which I'll just mention very briefly. Let's start with the fatalistic solution. There is and this is a very recent one, and it's probably the most exotic I've heard. And basically, it says, in effect, that nature conspires to set as it were, the initial conditions under which you do any experiment in such a way that quantum mechanics itself never produces these peculiar states. Now, nature has to conspire in a very, very peculiar way to do that. And, well, if you did believe that, I think you'd be, as it were, you'd be forced to an extremely fatalistic point of view. No experimenter could ever choose to do something really of his or her own free will. Nature would somehow conspire to get this peculiar result. That's a very peculiar one. Another one which is being, to some extent, considered seriously is what I call a mentalistic solution, which says, yeah, sure, take quantum mechanics seriously. Schrödinger's cat really is in this funny state until you look at it. But when a human being, human consciousness, looks at the state of the cat, then suddenly one of these two outcomes is selected. If you like, the realization occurs. So this then attributes to human consciousness a role in the interpretation of physics, which is, again, a peculiar idea, but, well, maybe we might someday have to take it seriously. The most exotic of all, perhaps, is the so-called many universes interpretation. Or the Everett-Wheeler interpretation, as it's sometimes called, which says, yes, indeed take quantum mechanics seriously. Schrödinger's cat is indeed in this funny state in which it's neither alive or dead. Moreover, and this is where it gets even more peculiar, if I actually look at it, and look at a particular cat, and think that I'm observing it to be, let us say, alive, then, nevertheless, there is a parallel world or a parallel universe which is equally real to the one I'm observing, in which I have seen the cat to be dead. So in other words, my subjective consciousness that I saw one result or the other is in some sense an illusion. There's always a parallel world going on which is said to have the same degree of reality as the world which we actually think we're experiencing. And then, of course, you might ask, well, surely that's ridiculous because, I might be on one world and you might be on another. But it turns out not. It turns out that as it were, the formalism of quantum mechanics itself guarantees that if I see a particular cat to be alive, you will also see her to be alive, etc., etc. So there's no, as it were, experimental contradiction. Nevertheless, this is a very, very peculiar interpretation. And personally, when people say that the unobserved worlds are as real as the ones we observe, it sounds like an English sentence. I do not know how to make sense out of those words. So the alternative now is to modify quantum mechanics as a description of the everyday world, and there have been, in other words, to assume that something else comes in at the level of the everyday world, which is not there at the level of atoms and molecules, and is such as to, as it were, force a definite outcome, to force each particular cat to be either alive or dead. And very briefly, since I'm running out of time, I won't say much in detail about that, but I will just mention that, to an extent, it is possible to test this kind of idea, and to test more generally the idea that macroscopic objects always are in definite macroscopic states. Now, it's fairly clear that you can't do this by looking at them, because if you look at them, automatically they always are in definite states. So you've got to do it indirectly by asking what would be the consequences if they were in this funny indeterminate state, this funny superposition state, at some intermediate point. And the answer is you do get different results. And in the last 10 years or so, there have been a series of experiments which have been begun to test as to whether you do get these funny so-called quantum superpositions of macroscopically distinct states. Now, they don't involve cats. The animal protection societies wouldn't allow it for a start, and in any case, there are all sorts of practical difficulties in dealing with cats. But they do involve things which are reasonably large. I mean, they can actually be seen with the naked eye, and they involve the possibility of currents flowing one way or flowing the other way. Under appropriate conditions, if you take quantum mechanics seriously, it predicts that you will not definitely have a current flowing clockwise or a current flowing anti-clockwise, but you will be in this peculiar state where both possibilities are represented. And these really are macroscopically distinct states. They correspond to something like 10 to the 23 electrons behaving differently in the two cases. And this experiment is currently being set up by an Italian group of Diambrini, Palazzi and co-workers, and right now it's still at the construction stage. And the idea is basically that you should be able to tell, at least in principle, by looking at the subsequent behavior, whether at a particular time the system was indeed in this funny superposition state, or whether it, as it were, had definitely chosen to be in one state or the other. As I say, this is near to Schrödinger's cat as you're likely to get in practice in the next decade or so, I imagine. Now, one can imagine three possible outcomes of this experiment. The first is the rather disappointing one, that the experiment in practice turns out to be impossible in the sense that the two hypotheses, namely that it's in this funny state or that it's definitely, as it were, chosen one alternative or the other, those two would in practice give the same experimental predictions. Too much noise around, if you like. That would be disappointing, but I don't think the whole thing would have been a waste of time because we'll have learned a lot along the way. The second possibility is that the experiment verifies the predictions of quantum mechanics and thereby refutes what I call macro-realism, which is the statement that at this kind of everyday level, things always have to do one thing or the other. They can't be in this funny indeterminate state. And I think most physicists probably, if asked to bet, would bet that this is what's going to happen, and that we'll just have to take quantum mechanics seriously at the everyday level, much distasteful as it is. The third possibility I think is the most fascinating. It could be that the experiment will actually come out in favour of macro-realism and thereby refute quantum mechanics as a complete description of the everyday world. Now, I can say right away, if that were to be the case with the first experiment, no one would believe it. There'd be all sorts of people pointing out there's all sorts of experimental errors and errors in the theoretical analysis and so on and so forth. But let's imagine, just for the sake of argument, that this experiment is repeated in 6 different labs at 6 different longitudes funded by 6 different agencies, etc., and it still gives these results. And moreover, that all the theoretical loopholes have been plugged, which is possible, although it would be difficult. What would we then have to conclude? I think we have to conclude something very, very interesting. You remember that the reason that we believed that quantum mechanics was the whole truth about the world at the everyday level was basically that we believe that atoms and molecules are brilliantly described by quantum mechanics, and that since big things, things like this desk or the lamp or me, are made up of atoms and molecules, therefore quantum mechanics should, in principle, completely describe matter at the everyday level. If that turns out not to be the case experimentally, then we are forced to a radical revision of the sort of reductionist prejudice that we've had for the last 300 years, namely that because big things are made of little things, the behaviour of the big things must be, in principle at least, completely explainable in terms of the behaviour of the smaller things they're made of. And that would certainly be, I think, very shocking to most of us. It would also be very exciting. And so I think, you know, if you think about it, you can see which of these three outcomes I am secretly hoping for. But please, at least when I'm sober, don't ask me to bet on the outcome. Thank you. Yes, I think.